The morning of March 15, 1973, begins like any other at the Bayou Chemical Processing Complex in southern Louisiana. 47 workers clock in for their shifts, unaware that by 11:47 a.m., 13 of them will be dead, buried beneath tons of twisted metal and concrete, their bodies never to be recovered. 23 others will fight for their lives in intensive care units across 3 parishes, while 11 more suffer injuries that will haunt them forever. All because a routine maintenance procedure becomes a catastrophic failure that claims 13 lives in less than 4 minutes. If you want to understand how this tragedy claimed so many lives and changed industrial safety forever, subscribe to this channel. This episode is a fictionalized reconstruction inspired by real chemical industry accidents and industrial safety investigations. Names, locations, and specific events have been created for storytelling purposes. The Bayou Chemical Processing Complex sprawls across 97 acres of Louisiana wetland, 23 miles southeast of Baton Rouge. Spanish moss drapes from ancient cypress trees that ring the facility's perimeter, their gnarled roots disappearing into brackish water that reflects the towering distillation columns and storage tanks. The air carries the perpetual smell of petroleum byproducts mixed with the earthy richness of bayou mud. March temperatures hover in the mid-70s, with humidity that makes coveralls stick to skin and safety equipment feel twice as heavy. This facility represents the heart of America's chemical revolution, processing crude oil derivatives into the building blocks of modern life. Polyethylene pellets, benzene compounds, and industrial solvents flow through miles of piping that snake between reactor vessels standing 8 stories tall. The complex operates 24 hours a day, 365 days a year, feeding the growing demand for plastics, synthetic materials, and chemical intermediates that fuel the nation's economic expansion. The morning shift arrives to the familiar symphony of industrial operation. Pumps hum with mechanical precision, steam vents release periodic clouds of superheated vapor, and the distant rumble of truck traffic carries raw materials in and finished products out. Workers navigate concrete pathways between towering equipment, their hard hats bobbing among forests of pipes, valves, and instrumentation that monitor temperatures, pressures, and flow rates with electronic vigilance. The facility's location in Louisiana's chemical corridor provides strategic advantages. Deep water access allows massive tankers to deliver crude oil directly to the complex's marine terminal, while rail connections and highway access ensure efficient distribution of finished products. The Mississippi River system offers transportation to markets throughout the Midwest, making this location economically vital for Petrogulf Industries, the Texas-based corporation that owns and operates the facility. Local communities have grown alongside the chemical industry, with entire families working different shifts at various plants along the river. The Bayou Complex employs nearly 300 people directly, with hundreds more jobs in supporting industries. School districts, hospitals, and municipal services depend on tax revenue generated by chemical processing, creating an economic ecosystem where industrial success and community prosperity intertwine. Weather patterns in southern Louisiana create unique operational challenges. High humidity accelerates corrosion of metal components, while frequent thunderstorms and occasional hurricanes test the resilience of equipment and safety systems. The facility's emergency procedures account for everything from minor equipment malfunctions to major weather events, with detailed protocols for protecting both personnel and equipment during various scenarios. The Bayou Chemical Processing Complex traces its origins to 1959, when Petrogulf Industries recognized the strategic value of Louisiana's chemical corridor. Construction began on what would become one of the region's largest petrochemical facilities, designed to process increasingly complex chemical reactions as the industry evolved beyond basic refining into sophisticated synthetic chemistry. Initial operations focused on relatively simple processes, converting crude oil fractions into basic chemical feedstocks. Success in these early ventures encouraged expansion, and by 1965, the facility had grown to include advanced polymerization units capable of producing high-grade plastics and synthetic materials. Each expansion brought new technologies, new processes, and new challenges for maintaining safe operations across an increasingly complex industrial system. The facility's safety record through the 1960s remained relatively clean, with only minor incidents requiring medical attention or brief operational shutdowns. Management prided itself on maintaining industry-standard safety protocols, conducting regular training sessions, and investing in protective equipment for workers. Monthly safety meetings addressed emerging concerns, and the facility's safety committee included representatives from each operational unit. However, the rapid expansion of the early 1970s began to strain both systems and personnel. New equipment installations often occurred while existing units remained operational, creating complex coordination challenges. Maintenance schedules became increasingly difficult to coordinate as production demands intensified, and the facility's workforce expanded faster than training programs could accommodate new personnel. Recent incidents had begun to raise concerns among experienced workers and supervisors. In January 1973, a pressure relief valve failure in the benzene unit resulted in an evacuation and 3 workers requiring treatment for chemical exposure. February brought a steam line rupture that scalded 2 maintenance technicians, though neither injury proved life-threatening. These incidents, while not catastrophic, indicated growing stress on aging systems and increasingly complex operational demands. Regulatory oversight in 1973 remained limited compared to modern standards. The Occupational Safety and Health Administration had been established only 2 years earlier, and comprehensive chemical industry regulations were still under development. Facility inspections occurred annually at best, with most safety oversight left to company policies and industry self-regulation. Environmental protections were similarly limited, with most focus on preventing obvious pollution rather than comprehensive risk assessment. The facility's maintenance records from early 1973 reveal a pattern of deferred repairs and delayed inspections. Budget pressures to maintain production schedules often resulted in postponing non-critical maintenance until planned shutdown periods. Critical safety systems received priority attention, but secondary systems and backup equipment sometimes operated beyond recommended service intervals. Training programs at the Bayou Complex followed industry standards of the era, emphasizing hands-on experience and mentorship from veteran workers. New employees typically spent several months learning basic procedures before advancing to more complex operations. However, the rapid expansion of operations meant that some workers advanced to supervisory roles faster than traditional timelines would suggest, creating potential gaps in experience and expertise. The workers who report for duty on March 15, 1973, represent a cross-section of Louisiana's industrial workforce. Supervisor Robert Chun, 42, brings 15 years of chemical processing experience and a reputation for methodical attention to detail. His wife Patricia and 2 teenage children expect him home for dinner, as they have for thousands of previous shifts. Chun oversees Unit 7, the facility's newest polyethylene production line, installed just 8 months earlier. Operator Maria Santos, 28, recently earned promotion to lead operator after demonstrating exceptional skill in managing complex chemical processes. She grew up in a family where industrial work provided stability and advancement opportunities, and she takes pride in being one of the facility's few female operators. Santos specializes in the distillation systems that separate chemical compounds with precise temperature and pressure control. Maintenance supervisor James Mitchell, 37, started at the facility as an apprentice mechanic 12 years ago and worked his way up through every system in the complex. His expertise in the facility's intricate piping systems makes him invaluable for troubleshooting problems that stump younger technicians. Mitchell's crew handles the most challenging repairs, often working in confined spaces and hazardous environments. Chemical engineer David Nguyen, 25, joined the facility 6 months ago after completing his degree at Louisiana State University. His theoretical knowledge of chemical processes complements the practical experience of veteran operators, and he shows promise for eventual advancement to plant management. Nguyen works closely with production supervisors to optimize process efficiency while maintaining safety standards. Operator William Rodriguez, 41, brings 20 years of experience from various chemical facilities across Texas and Louisiana. His calm demeanor during emergency situations has earned respect from colleagues and supervisors alike. Rodriguez operates the central control systems that monitor and adjust processes throughout the facility, requiring constant vigilance and quick decision-making skills. Maintenance technician Charles Thompson, 39, specializes in the complex instrumentation systems that monitor chemical processes. His ability to diagnose and repair electronic control systems keeps production running smoothly and safely. Thompson's work often requires entering confined spaces and working with potentially dangerous chemical environments. Quality Control Supervisor Linda Harrison, 34, ensures that chemical products meet strict specifications before leaving the facility. Her laboratory work requires handling samples of various chemicals and maintaining precise analytical equipment. Harrison's attention to detail prevents defective products from reaching customers and identifies potential process problems before they become serious. Operator Frank Delacroix, 45, represents the facility's connection to local Louisiana culture, with family roots in the region stretching back generations. His knowledge of local weather patterns and environmental conditions helps predict operational challenges. Delacroix operates the facility's storage and transfer systems, managing the movement of thousands of gallons of chemicals daily. Maintenance technician Samuel Foster, 29, recently completed specialized training in high-pressure system repairs. His mechanical skills and willingness to tackle difficult repairs make him a valuable team member. Foster's work includes maintaining the critical safety systems that protect workers and equipment during emergency situations. These 9 individuals, along with 4 others working various positions throughout the facility, will become the 13 workers whose bodies are never recovered from the wreckage that follows. Their families will wait for news that never comes. Their colleagues will search through twisted metal and concrete debris, and their deaths will ultimately transform industrial safety practices across the chemical industry. The early morning hours of March 15th proceed with routine efficiency. Night shift operators complete their final rounds, checking equipment status and recording process parameters in logbooks that will later become crucial evidence. Temperatures throughout the facility remain within normal ranges. Pressure readings show stable operation, and chemical flow rates match production targets. Shift change occurs at 7 a.m. with the standard briefing between outgoing and incoming supervisors. Night shift supervisor Thomas Walsh reports no significant issues, though he mentions a minor pressure fluctuation in Unit 7's reactor system around 3 a.m. The fluctuation corrected itself within normal parameters, but Walsh recommends monitoring the situation closely. Incoming supervisor Robert Chun acknowledges the information and adds Unit 7 monitoring to his morning priorities. Weather conditions appear favorable for the planned maintenance activities scheduled throughout the day. Clear skies and moderate temperatures will allow outdoor work to proceed safely, while low humidity reduces static electricity risks when working with volatile chemicals. Wind speeds remain light, minimizing concerns about chemical vapor dispersion should any minor releases occur during maintenance procedures. The maintenance schedule for March 15th includes routine inspections of pressure relief systems, calibration of electronic monitoring equipment, and replacement of worn gaskets in several piping connections. Most significantly, the schedule calls for testing emergency shutdown systems in Unit 7, the facility's newest production line. This testing requires temporarily disabling certain safety interlocks while verifying that backup systems function properly. Production targets for the day call for processing 47,000 gallons of chemical feedstock through various reaction and purification stages. Market demand for the facility's products remains strong, creating pressure to maintain efficient operations while conducting necessary maintenance activities. Scheduling coordinators work to balance production requirements with safety considerations, though the complexity of these decisions sometimes creates unforeseen conflicts. Equipment status reports from the previous week indicate that most systems operate within normal parameters, though several items require attention. A pressure relief valve in Unit 7 shows signs of gradual deterioration, with relief pressure drifting slightly higher than design specifications. While still within acceptable limits, the valve is scheduled for replacement during the next planned shutdown in 6 weeks. Chemical inventory levels appear adequate for planned production, with sufficient raw materials to maintain operations through the weekend. Storage tank levels remain within safe operating ranges, and transfer systems show no signs of unusual wear or malfunction. However, Increased production demands have resulted in more frequent tank transfers, placing additional stress on pumping systems and transfer piping. Communication systems throughout the facility undergo daily testing to ensure reliable emergency communications. Radio networks, telephone systems, and emergency alarm circuits all function properly, providing multiple backup methods for coordinating activities and responding to potential problems. However, the facility's expansion has created some coverage gaps in remote areas where radio signals occasionally fade. By 9 a.m., all systems appear ready for the day's planned activities. Operators complete their startup procedures, maintenance crews gather tools and materials for scheduled work, and supervisors coordinate activities to minimize interference between production and maintenance operations. The morning proceeds with the methodical precision that characterizes successful chemical processing operations. Unit 7, the facility's newest and most sophisticated production line, represents the cutting edge of 1973 chemical processing technology. Installed at a cost of $12 million, the unit can produce 15 different grades of polyethylene using advanced catalyst systems and precise temperature control. The unit's reactor vessel stands 7 stories tall, containing chemical reactions at temperatures exceeding 800 degrees Fahrenheit and pressures reaching 400 pounds per square inch. The unit's design incorporates multiple safety systems intended to prevent dangerous conditions from developing. Pressure relief valves automatically vent excess pressure to a safe disposal system. Temperature monitors trigger cooling systems when readings exceed safe limits, and emergency shutdown procedures can halt all chemical reactions within 90 seconds. Backup power systems ensure that safety equipment continues operating even during electrical failures. However, Unit 7's complexity creates maintenance challenges that older, simpler systems do not present. The unit contains over 2,000 individual valves, gauges, and control devices, each requiring periodic inspection and calibration. Computer-controlled systems monitor hundreds of process variables simultaneously, but these electronic systems prove sensitive to humidity, temperature variations, and electrical interference common in industrial environments. Recent performance data from Unit 7 indicates generally successful operations since startup 8 months ago, though several minor issues have emerged. Chemical yields occasionally fall below design specifications, suggesting that reaction conditions may not be perfectly optimized. Catalyst consumption exceeds projected levels, indicating possible inefficiencies in the reaction process. Most concerning, pressure relief valves have activated more frequently than design calculations predicted. The scheduled maintenance for March 15 focuses specifically on Unit 7's emergency shutdown systems. These systems must be tested monthly to ensure they can halt dangerous chemical reactions quickly and safely. The testing procedure requires temporarily disabling normal safety interlocks, while technicians verify that backup systems respond properly to emergency signals. At 10:15 a.m., Maintenance Supervisor James Mitchell begins the complex procedure for testing Unit 7's emergency shutdown systems. The process starts with isolating the reactor vessel from chemical feedstock supplies, allowing existing chemical reactions to reach completion while preventing new reactions from starting. This isolation procedure normally takes 20 to 30 minutes, depending on the specific chemicals being processed. Chemical engineer David Nguyen monitors reactor conditions from the central control room, watching temperature and pressure readings as the isolation procedure progresses. Reactor temperature begins declining slowly as chemical reactions consume available feedstock, while pressure readings remain stable within normal operating ranges. All indicators suggest that the isolation procedure proceeds normally. Operator Maria Santos coordinates with Mitchell's maintenance crew to ensure that all chemical transfer systems properly isolate Unit 7 from the rest of the facility. This isolation prevents chemicals from flowing between Unit 7 and other production units during the testing procedure, reducing risks to personnel working throughout the facility. Santos confirms that isolation valves close completely and that no chemical flow occurs between systems. The testing procedure requires disabling Unit 7's primary emergency shutdown system while verifying that the backup system functions properly. This creates a temporary condition where normal safety protections are reduced, though backup systems and manual controls remain available. Detailed procedures specify exactly how long safety systems may remain disabled and what monitoring procedures must be maintained during testing. At 10:45 a.m., Mitchell's crew begins the critical phase of disconnecting electrical controls for the primary emergency shutdown system. This work requires entering a confined electrical enclosure located 30 feet above ground level, accessible only through a narrow maintenance platform. Two technicians, Charles Thompson and Samuel Foster, begin the delicate process of disconnecting control circuits while maintaining power to monitoring systems. Unknown to the maintenance crew, the pressure relief valve that had shown signs of gradual deterioration during previous weeks has continued to degrade. The valve's internal spring mechanism, weakened by months of exposure to corrosive chemicals and high temperatures, begins to lose its ability to maintain proper sealing pressure. This degradation accelerates as chemical reactions in the reactor vessel create pressure fluctuations that stress the weakening valve components. Operator William Rodriguez, monitoring Unit 7's systems from the central control room, notices slight pressure variations in the reactor vessel. These variations appear minor and within normal ranges for equipment undergoing maintenance procedures. However, the pressure fluctuations indicate that the deteriorating relief valve has begun allowing small amounts of chemical vapor to escape from the reactor system. Chemical engineer David Nguyen reviews historical data from Unit 7's operation, searching for patterns that might explain the recent pressure fluctuations. His analysis reveals a gradual increase in relief valve activations over the past month, suggesting progressive deterioration of valve components. However, this information does not immediately indicate an imminent failure that threatens worker safety. At 11:20 a.m., maintenance technician Charles Thompson reports completion of the electrical disconnection procedures for Unit 7's primary emergency shutdown system. The backup system shows green status indicators, and initial testing suggests that emergency shutdown capabilities remain functional through the secondary control circuits. However, the backup system has never been tested under actual emergency conditions with chemical reactions occurring in the reactor vessel. The deteriorating pressure relief valve reaches a critical failure point as chemical pressures in the reactor vessel fluctuate during the testing procedure. Internal valve components, weakened beyond their design limits, suddenly fracture under routine pressure variations that should not cause failure. The fracture creates an immediate path for high-pressure chemical vapors to escape from the reactor system into the surrounding air. Operator Maria Santos first notices the valve failure when pressure readings in Unit 7 begin dropping rapidly. Within 30 seconds, reactor pressure falls from normal operating levels to dangerously low readings that indicate a significant chemical release. Santos immediately attempts to activate emergency shutdown procedures, but discovers that the primary shutdown system remains disabled for testing purposes. Chemical vapors escaping from the failed relief valve create an immediate hazard to personnel working near Unit 7. The vapors, containing toxic and flammable compounds at concentrations far exceeding safe exposure limits, begin forming a dangerous cloud around the reactor vessel. Winds carry the vapor cloud toward the maintenance platform where Thompson and Foster continue working on electrical systems. David Nguyen recognizes the severity of the situation and attempts to activate Unit 7's backup emergency shutdown system from the central control room. However, the backup system, designed as a secondary measure rather than a primary control method, responds more slowly than normal shutdown procedures. Critical seconds pass while backup systems attempt to halt chemical reactions and isolate the damaged reactor vessel. At 11:35 a.m., the chemical vapor cloud reaches sufficient concentration to create an explosive mixture with atmospheric oxygen. The exact ignition source remains unclear, though investigators later identify several possibilities including static electricity from maintenance equipment, electrical sparks from control circuits, or heat from nearby process equipment. The ignition occurs without warning, creating a massive explosion that destroys Unit 7's reactor vessel and surrounding equipment. The explosion generates a pressure wave that travels at supersonic speeds through the facility, shattering windows, collapsing structures, and hurling debris across hundreds of yards. The reactor vessel, weighing over 40 tons when empty, disintegrates into fragments that become deadly projectiles. Concrete structures designed to withstand normal chemical processing loads prove inadequate against the explosive forces generated by the chemical detonation. Maintenance technicians Thompson and Foster, working on the electrical platform 30 feet above ground, have no opportunity to escape the initial explosion. The platform, constructed of steel grating and support beams, collapses instantly when struck by the pressure wave and flying debris. Both men fall into the wreckage of destroyed equipment, where their bodies become buried beneath tons of twisted metal and concrete. Supervisor Robert Chun, conducting his routine inspection rounds near Unit 7, becomes trapped when the explosion destroys the concrete structure housing the unit's control systems. The building's walls, designed to contain minor chemical releases, cannot withstand the explosive forces and collapse inward. Chin's body is never recovered from the rubble that fills the building's foundation. Operator Maria Santos, attempting to reach emergency controls in Unit 7's auxiliary building, is caught in the secondary explosion that occurs when the initial blast ignites chemical storage tanks adjacent to the reactor. The auxiliary building, constructed with lighter materials than the main reactor housing, disintegrates completely. Santos and 3 other workers in the building disappear beneath the debris field that spreads across nearly an acre. The explosion's effects cascade through adjacent areas of the facility as flying debris damages equipment and piping systems throughout the complex. Secondary explosions occur as damaged chemical lines ignite, creating additional hazards for workers attempting to evacuate. The facility's emergency alarm system, partially damaged by the initial blast, provides inconsistent warnings to personnel in outlying areas. Chemical engineer David Nguyen, protected by the central control room's reinforced construction, survives the initial explosion but faces immediate challenges in coordinating emergency response efforts. Communication systems suffer extensive damage, making it difficult to determine the extent of casualties and coordinate evacuation procedures. Nguyen works frantically to shut down chemical processes throughout the facility while emergency responders mobilize. Within 4 minutes of the initial pressure relief valve failure, 13 workers lie dead or dying beneath the wreckage of Unit 7. The explosion has created a debris field covering nearly 2 acres, with some pieces of equipment thrown over 300 yards from their original locations. Chemical fires burn throughout the wreckage, making immediate rescue attempts impossible and threatening to spread to other parts of the facility. Emergency response procedures activate immediately following the explosion, though the extent of damage creates unprecedented challenges for rescue teams. The facility's internal emergency response team, trained for chemical spills and minor fires, faces a disaster far beyond their preparation and equipment capabilities. External emergency services receive notification within minutes, but the remote location and specialized nature of chemical hazards require time to mobilize appropriate resources. The Iberville Parish Fire Department dispatches its hazardous materials team within 12 minutes of the initial explosion report. However, the team's equipment and training focus on transportation accidents involving single chemical spills rather than major industrial disasters with multiple chemical hazards and structural collapse. Additional specialized resources must be requested from Baton Rouge and New Orleans, creating delays in mounting effective rescue operations. Louisiana State Police coordinate the emergency response effort, establishing command posts and communication networks to manage the complex operation. The explosion's impact extends beyond the immediate facility, with debris and chemical releases affecting nearby waterways and residential areas. Evacuation orders affect over 2,000 residents within a 3-mile radius, creating additional coordination challenges. Emergency medical services face the grim reality that most casualties from the explosion require immediate trauma care beyond the capabilities of local hospitals. Helicopter ambulances transport the most seriously injured workers to specialized trauma centers in Baton Rouge and New Orleans, while local medical facilities struggle with the sudden influx of patients suffering from chemical exposure, burns, and blast injuries. The facility's emergency response plan, designed for gradual escalation of incidents, proves inadequate for the immediate catastrophic failure that destroys Unit 7. Communication systems damaged by the explosion prevent effective coordination between different areas of the facility, while chemical fires and unstable structures make many areas inaccessible to rescue teams. Search and rescue operations begin within hours of the explosion, though unstable structures and ongoing chemical hazards severely limit access to the areas where workers remain missing. Specialized equipment for moving heavy debris arrives from construction companies throughout Louisiana, while chemical experts work to identify and neutralize hazardous materials that continue burning or releasing toxic vapors. Recovery efforts focus initially on areas where survivors might remain trapped but alive, though the violence of the explosion makes survival unlikely for anyone caught in the immediate blast zone. Thermal imaging equipment, still experimental in 1973, provides limited assistance in locating potential survivors beneath the debris. Most search efforts rely on systematic removal of wreckage and careful listening for any sounds that might indicate trapped workers. The immediate aftermath reveals the full scope of the tragedy that has befallen the Bayou Chemical Processing Complex. 13 workers are confirmed dead or missing and presumed dead, with their bodies lost beneath tons of debris that will take weeks to remove. 23 others suffer serious injuries requiring immediate hospitalization, while 11 more receive treatment for chemical exposure and minor trauma before being released. The death toll represents the worst industrial accident in Louisiana's chemical industry to that date, exceeding previous incidents by a significant margin. The workers who died include experienced supervisors, skilled operators, and maintenance technicians whose knowledge and expertise cannot be easily replaced. Their deaths leave families without breadwinners and the facility without critical personnel needed for safe operation. Medical examiner reports, released weeks later after body recovery operations conclude, indicate that most victims died instantly from massive trauma caused by the explosion and structural collapse. The few workers whose bodies are recovered show evidence of fatal injuries from flying debris, structural collapse, and explosive forces that no safety equipment could have prevented. Robert Chin's body is eventually recovered from beneath the collapsed control building, confirming that he died instantly when the structure disintegrated. Maria Santos and the 3 workers trapped in the auxiliary building are found together, suggesting they were attempting to evacuate when the secondary explosion occurred. Charles Thompson and Samuel Foster remain buried beneath the wreckage of the electrical platform, their bodies recovered only after specialized equipment removes the twisted steel and concrete. The economic impact of the disaster extends far beyond the immediate facility, affecting the entire Louisiana chemical industry and related businesses. The Bayou Complex, which employed nearly 300 workers and generated millions of dollars in annual economic activity, remains completely shut down while investigations proceed and rebuilding decisions are made. Hundreds of additional jobs in supporting industries face uncertainty as the facility's future remains unclear. Environmental consequences from the explosion include chemical contamination of nearby waterways, soil contamination from spilled and burned chemicals, and air quality concerns from the massive chemical fire that burned for over 18 hours. State environmental officials begin monitoring programs to assess long-term environmental damage and develop cleanup strategies for affected areas. Community impact reaches beyond economic concerns as families struggle with the sudden loss of loved ones and the uncertainty surrounding the facility's future. Schools, churches, and community organizations mobilize to provide support for affected families, while local government officials work to understand the broader implications of the disaster for regional economic development. Insurance claims related to the explosion eventually exceed $47 million. Including property damage, business interruption, wrongful death settlements, and environmental cleanup costs. The financial impact forces Petrogulf Industries to reevaluate its operations throughout the chemical corridor and implement significant changes in safety procedures and equipment maintenance. Media coverage of the disaster focuses national attention on chemical industry safety practices and the adequacy of existing regulations. Television news reports show dramatic footage of the burning facility and interviews with survivors and family members, bringing the human cost of industrial accidents into American living rooms with unprecedented immediacy. The investigation into the Louisiana Chemical Plant Explosion begins within hours of the blast, as federal and state agencies mobilize teams of specialists to determine what caused 13 workers to lose their lives. The National Transportation Safety Board, though primarily focused on transportation accidents, provides expertise in explosion analysis and accident reconstruction. The Occupational Safety and Health Administration, still developing its capabilities for major industrial accident investigation, assigns its most experienced inspectors to the case. Louisiana State Fire Marshals lead the initial investigation, working to determine the explosion's origin point and sequence of events. Their preliminary findings identify Unit 7 as the source of the initial blast, with secondary explosions occurring as the fire spread to adjacent chemical storage and processing equipment. However, determining the specific cause of the pressure relief valve failure requires detailed metallurgical analysis beyond state capabilities. Federal investigators arrive within 24 hours, bringing specialized equipment for analyzing explosion damage and chemical residues. The investigation team includes chemical engineers, metallurgical specialists, safety experts, and accident reconstruction specialists who begin the painstaking process of documenting evidence and interviewing survivors. The pressure relief valve identified as the initial failure point undergoes extensive laboratory analysis at federal facilities in Washington. Metallurgical examination reveals that the valve's internal spring mechanism suffered progressive corrosion damage over several months, gradually reducing its ability to maintain proper sealing pressure. The corrosion resulted from exposure to chemical compounds that exceeded the valve's design specifications. Chemical analysis of residues found throughout the blast area confirms that Unit 7 was processing a particularly aggressive chemical mixture at the time of the explosion. The mixture, designed to produce a new grade of polyethylene with enhanced properties, created more corrosive conditions than standard production runs. However, the facility's maintenance procedures had not been updated to account for the increased corrosion potential. Examination of maintenance records reveals that the failed pressure relief valve was scheduled for replacement during a planned shutdown 6 weeks after the explosion occurred. The valve had shown signs of deterioration during previous inspections, but remained within acceptable operating parameters according to existing guidelines. Investigators question whether more frequent inspection intervals might have detected the progressive failure before it reached catastrophic levels. The emergency shutdown system testing procedure receives intense scrutiny as investigators work to understand why backup safety systems failed to prevent the disaster. Analysis reveals that the backup shutdown system, while functional, operated significantly slower than the primary system and could not respond quickly enough to contain the rapid pressure loss from the failed valve. Witness interviews with surviving workers provide crucial information about the sequence of events leading to the explosion. Multiple witnesses confirmed that pressure fluctuations began approximately 25 minutes before the explosion, though these fluctuations appeared minor and within normal operating ranges. No worker reported recognizing the pressure variations as indicating imminent catastrophic failure. David Nguyen's detailed testimony proves particularly valuable, as his position in the central control room provided comprehensive monitoring of Unit 7 systems during the critical period. His account confirms that backup emergency systems activated properly, but could not halt chemical reactions quickly enough to prevent the explosive chemical release. Investigators examined the facility's training programs to determine whether workers possessed adequate knowledge to recognize and respond to the developing emergency. Analysis reveals that training focused primarily on gradual equipment failures and routine maintenance procedures, with limited coverage of rapid catastrophic failures like the pressure relief valve rupture. The investigation expands to examine similar pressure relief valves throughout the chemical industry, revealing that the specific valve model involved in the explosion had experienced failures at other facilities. However, no centralized reporting system existed to share information about equipment failures across different companies and facilities. Engineering analysis of Unit 7's design reveals that the unit's complexity created potential failure modes that were not fully understood when the system was installed. The interaction between multiple chemical processes, electronic control systems, and safety equipment created scenarios where single component failures could cascade into major disasters. Computer modeling of the explosion, using techniques developed for military and aerospace applications, confirms that the chemical release created explosive conditions within 90 seconds of the initial valve failure. The modeling indicates that even perfect emergency response procedures could not have prevented the explosion once the valve failed catastrophically. Final investigation reports, released 14 months after the explosion, identify the progressive corrosion failure of the pressure relief valve as the primary cause of the disaster. Contributing factors include inadequate maintenance procedures for the aggressive chemical environment, insufficient backup emergency systems, and lack of industry-wide information sharing about equipment failures. The investigation concludes that the 13 deaths resulted from a combination of equipment failure, procedural inadequacies, and systemic problems in chemical industry safety practices. Investigators emphasize that the disaster was preventable through better equipment maintenance, improved emergency procedures, and more robust safety system design. Legal proceedings following the explosion span over 5 years and involved dozens of lawsuits filed by victims' families, injured workers, and affected community members. Wrongful death lawsuits filed by the families of the 13 workers who died seek damages for lost income, medical expenses, and pain and suffering. These cases ultimately result in settlements totaling over $12 million. Petrogulf Industries faces criminal charges related to workplace safety violations, though these charges are eventually reduced to civil penalties after the company agrees to implement comprehensive safety improvements throughout its operations. The company pays over $3 million in fines and penalties, representing one of the largest workplace safety settlements in Louisiana history at that time. Personal injury lawsuits filed by surviving workers focus on long-term health effects from chemical exposure and trauma from the explosion. Several workers develop respiratory problems and other health issues attributed to chemical exposure during the disaster. These cases result in additional settlements and ongoing medical monitoring programs. The facility itself undergoes complete reconstruction following the explosion, with new safety systems designed to prevent similar disasters. Unit 7 is never rebuilt, and the area where it stood becomes a memorial garden honoring the 13 workers who died. The rebuilt facility incorporates lessons learned from the investigation, including redundant safety systems and improved emergency procedures. Regulatory changes prompted by the disaster include new requirements for pressure relief valve inspection and maintenance, mandatory reporting of equipment failures across the chemical industry, and enhanced emergency response training for workers in chemical processing facilities. These changes influence chemical industry practices nationwide and establish precedents for future safety regulations. The Occupational Safety and Health Administration uses lessons learned from the investigation to develop new standards for chemical processing safety, including requirements for more frequent equipment inspections and enhanced emergency shutdown capabilities. These standards become models for chemical industry safety regulations worldwide. Environmental cleanup efforts continue for over 2 years, with soil and water remediation programs addressing contamination from the explosion and chemical releases. The cleanup costs exceed $15 million and establish new standards for environmental response to industrial accidents. The facility's workforce rebuilds slowly, with extensive new training programs designed to prevent similar disasters. New workers receive training in recognizing equipment failure symptoms and responding to emergency situations. The training programs become models for other chemical facilities throughout Louisiana and beyond. Insurance industry changes following the explosion include new requirements for chemical facility risk assessments and enhanced safety equipment standards. Insurance companies begin requiring more detailed safety inspections and equipment maintenance programs before providing coverage for chemical processing operations. The long-term impact of the Louisiana Chemical Plant Explosion extends far beyond the immediate tragedy, fundamentally transforming chemical industry safety practices and regulatory oversight. The 13 workers who died become symbols of the human cost of inadequate safety measures, and their deaths drive systematic changes that save countless lives in subsequent decades. Professional engineering societies develop new standards for pressure relief valve design and maintenance, specifically addressing the corrosion problems that caused the initial failure. These standards require more frequent inspections, improved material selection, and enhanced monitoring systems for critical safety equipment. Chemical industry trade associations establish information sharing networks to communicate equipment failure data across different companies and facilities. This system enables rapid identification of potential problems and coordinated responses to equipment defects, preventing similar failures from occurring at multiple locations. University engineering programs incorporate case studies of the explosion into their curricula, ensuring that future chemical engineers understand the importance of safety system design and maintenance. The disaster becomes a standard example of how single component failures can cascade into major catastrophes without proper safeguards. Emergency response procedures throughout the chemical industry undergo major revisions based on lessons learned from the explosion. New procedures emphasize rapid shutdown capabilities, improved communication systems, and enhanced coordination with external emergency services. These improvements prove crucial in preventing casualties during subsequent industrial incidents. The memorial garden established at the site of Unit 7 becomes a pilgrimage destination for safety professionals and a reminder of the importance of vigilance in industrial operations. Plaques honor each of the 13 workers who died, listing their names, ages, and years of service. Annual memorial services bring together families, co-workers, and industry professionals to remember the victims and renew commitments to workplace safety. Safety culture changes throughout the chemical industry reflect the profound impact of the disaster on worker attitudes and management priorities. The explosion demonstrates that routine maintenance procedures can become matters of life and death, encouraging more careful attention to equipment condition and safety system functionality. Technological advances in monitoring and control systems, accelerated by lessons learned from the explosion, provide chemical facilities with better tools for detecting equipment problems before they become dangerous. Electronic monitoring systems, computer-controlled safety systems, and improved communication networks all contribute to enhanced safety capabilities. Current chemical processing facilities incorporate multiple layers of safety protection designed to prevent single-component failures from causing catastrophic accidents. Redundant safety systems, improved emergency procedures, and enhanced worker training all trace their origins to lessons learned from the 13 deaths at the Bayou Chemical Processing Complex. The families of the workers who died continue to advocate for industrial safety improvements, working with professional organizations and regulatory agencies to prevent similar tragedies. Their efforts ensure that the memory of their loved ones contributes to ongoing improvements in workplace safety. The Louisiana Chemical Plant Explosion of 1973 stands as a watershed moment in industrial safety, demonstrating how seemingly minor equipment failures can escalate into major disasters when safety systems prove inadequate. The 13 workers who died were not statistics, but individuals with families, dreams, and contributions to their communities. Robert Chin's methodical attention to detail, Maria Santos's determination to succeed in a male-dominated industry, James Mitchell's expertise in complex systems, and the dedication of their colleagues represented the human face of industrial work. Their deaths reveal the hidden vulnerabilities that exist in complex industrial systems, where the failure of a single component can trigger catastrophic consequences. The pressure relief valve that failed had operated successfully for months, showing only minor signs of deterioration that seemed manageable within existing maintenance schedules. Yet the valve's failure initiated a chain of events that overwhelmed multiple safety systems and killed 13 people within minutes. The explosion demonstrates how industrial accidents often result from the intersection of equipment failure, procedural inadequacies, and systemic problems rather than single dramatic causes. The pressure relief valve might have failed safely if emergency shutdown systems had operated faster, if backup safety systems had been more robust, or if maintenance procedures had detected the corrosion damage earlier. Instead, multiple small problems combined to create a disaster that claimed 13 lives. The investigation reveals how complex industrial systems can create failure modes that exceed the imagination of their designers and operators. Unit 7's sophisticated control systems and safety equipment represented the best technology available in 1973. Yet these systems proved inadequate when confronted with the rapid cascade of failures that followed the valve rupture. Perhaps most importantly, the disaster illustrates how industrial safety requires constant vigilance and continuous improvement rather than complacency about existing procedures and equipment. The workers who died were following established procedures and operating equipment that met all applicable standards. Yet these measures proved insufficient to protect their lives when confronted with an unexpected failure mode. The legacy of the 13 workers who died extends far beyond the immediate tragedy, influencing safety practices throughout the chemical industry and contributing to regulatory changes that protect thousands of workers today. Their deaths were not meaningless, but became catalysts for improvements that prevent similar tragedies from claiming other lives. Modern chemical facilities operate with safety systems and procedures that directly reflect lessons learned from the Louisiana explosion, ensuring that the sacrifice of these 13 workers contributes to ongoing protection of their industrial colleagues. Every pressure relief valve inspection, every emergency procedure drill, and every safety system upgrade carries forward the memory of workers who died because existing protections proved inadequate. If this story about preventable tragedy and lost lives gave you insight into why safety matters, leave your like and share with others who appreciate learning from fatal accidents so others might live.